Hey, this is Wang. Our paper title is Attentive Normalization for Conditional Image Generation. This is a joint work with Ying-Cong Chen, Xiangyu Zhang, Jian Sun, and Jiaya Jia. Conditional image generation means to produce realistic images based on a given condition. For natural images, they contain semantic correspondence such as the symmetry of panda ears, and such information are often distributed in long-range form. For most fully convolutional network-based generators, they usually do not work well on modeling images with complicated structures. The reason is that each layer in convolutional network is locally bounded, and the relation between distant locations like panda ears here relies on the Markov chain between convolutional layers. SelfAttention gain takes the first step to model long-range dependency in this task. The SelfAttention module requires computing the correlation between every 2 points in the feature maps. Thus, the computational costs are heavy as the feature map becomes large. In this paper, we normalize the input feature maps spatially according to the semantic layouts predicted from them. It improves the distance relationship in the input as well as preserving semantic spatially. Our method is formed by semantic layout learning and regional normalization. The former produces semantic-aware masks that divide the feature map into several parts. With semantic layout, spatial information propagation is conducted by the independent normalization in each region. Let's talk about semantic layout learning module first. We assume each image is composed of unsymmetrical entities. For each future point of the image is determined by at least one entity. Here we are interested in the way to group feature points of an image. We give n initial desired semantic entities and define their correlation to the feature point as their inner product. We aggregate the feature points into different regions based on the activation status with these entities. In our implementation, a convolutional layer with n filters is adopted as semantic entities. However, only with this component does not lead to reasonable training, since it tends to group all feature points with a single semantic entity. Besides, we have no protocol to ban useless semantic entities. From this perspective, we introduce a self-sampling branch providing a reasonable initial semantic layout estimate. It can prevent the trivial solution. Our self-sampling branch randomly selects n feature points from the input translated feature maps, acting as alternative for the semantic entities. They are activated when some entities become irrelevant with the input feature maps. This branch utilizes the correlation in the same feature maps to approximate the semantic layout. In the above figure, standard deviation computed from the areas highlighted by our predicted semantic layout is much lower than that from the whole feature map. In the below figure, the learned semantic entities can activate different regions of the feature maps. They both show the predicted semantic layout indicate regions with higher inner coherence in semantics. For its complexity analysis, attentive normalization consumes much less than a SelfAttention module. We evaluate our attentive normalization in class-conditional image generation on ImageNet. Compared with SelfAttention gain, our method yields lower FID and intra-FID. It shows our module performance comparably to SelfAttention, which verifies our module can improve class-conditional image generation performance. Also, we observe that our method can produce more diverse patterns on natural scenes or textures in this task, and categorical interpolation. Besides, it works well in generative image impinting, which is carried out on Paris Street View dataset. The impinting network using attentive normalization gives appealing visual performance regarding semantic structure and detailed texture. Thanks for watching.